In section 1.3, one of the things that we talked about was determining if a given vector was a linear combination of another set of vectors. And in that process of determining whether it is or not, we saw that we could squish together kind of the individual vectors that we were given into a matrix. So we're going to talk more about that here in section 1.4. And instead of having a vector equation, which we'll recap here, we have a matrix equation if we squish all those vectors into one matrix. So the definition sometimes can be a little bit confusing, but I'll give some explanation after I'm done. If A is an m by n matrix, so it's not a vector. The m and the n, typically, if we give those as letters, we don't mean for them to be ones. If we need it to be a vector, then we will say it's n by 1. It's just got one column. But if they're not ones, then we assume that this is a matrix with dimensions other than 1. If A is an m by n matrix with columns A sub 1, A sub 2, all the way out to A sub n. So these individual columns kind of represent the individual vectors that we had back in the last section. And if X is in Rn, remember we said all that means is it is a vector with n entries. Then the product of A and X, which there's no special really notation for products between matrices and vectors, is denoted by just AX, just like we would do in algebra class. This is the linear combination of the columns of A using the corresponding entries in X as weights. And when we describe them as weights, it makes it a little bit more kind of intuitive, or it's easier to see that how we could possibly use this in application problems. Those weights could be actual weight, they could be cost, could be a number of different things that we could use for actual applications. So if we actually write this out in algebra notation, A, we're only identifying the columns. There are a full column of numbers here, but we're just calling the entire first column A sub 1 and the entire second column A sub 2. And then that means our last column would be A sub n, because remember, this value right here tells us we have n columns. So within each of these columns, so A sub 1 is a column with m entries in it. So we've got m number of entries going down on each. We're only interested in talking about the columns because that's what we saw in section 1.3, is each of these individual columns represents a vector. Now, when I multiply this by vector x, and x is a variable, and we said it was in Rn, so that means there's n entries, so x1, x2, all the way down to xn. This is just another way to write the linear combination of the columns of A using the corresponding entries in X. So each column here in A matches up with an entry in X. So this gives us the linear combination A1 X1 plus A2 X2 all the way out to AN XN. And I'll show you a couple of examples of this. It's always a little bit easier when you have some actual matrices and some numbers to go along with this and see kind of how everything works out. So we could have, for right now, we're not going to use X's. We're just going to demonstrate how this distribution happens. Let's say we've got 205, negative 132. So that is our A matrix. This column is A sub 1. This column is A sub 2. This column is A sub 3. And then we have this other matrix, and we're going to say negative 4, 1, negative 2. So what our definition says up here is that this product is the linear combination of the columns of A using the corresponding entries in X as weights. So each column in matrix capital A, so I'm going to separate them out into vectors. We're kind of just going backwards from what we saw in section 3. Each of these columns goes with each of its corresponding weight from that vector that comes after. And since 1 doesn't have any sort of sign, that's automatically a plus. And then the last entry goes with the last column, and that's a minus 2. And we can actually keep working this out because this is just a scalar multiple here. And we said with scalar multiples, we'll just distribute the value inside. So that's going to be negative 8, 4. And then distributing a 1 is not going to change those values. It's still 0, 3. And then if I distribute a negative 2, then I'm going to change that to addition. That matrix becomes negative 10, negative 4. Now we've just got an addition problem with 3 matrices of the exact same size, and we said to do that, we just combine corresponding components. So they all have one column with 2 rows. So we're going to combine all of those first row numbers together, and we get negative 18. And we combine all of those second row numbers together, and we get 3. So because I used actual numbers in the x vector here, this works all the way down to a 1 by 2, or excuse me, a 2 by 1 column vector. There's just something that you need to make sure always matches to make this work. And they say it in the definition, but some people don't always catch up on it. A is an M by N matrix, and then X is an Rn. Those numbers have to match in order for this to work. I have to be able to match up every single entry in the column vector that comes second with a column in matrix A. And as long as the number of columns in A matches the number of entries in X, this will work. So let's look at one more that has a different size, just so we can see how this works. So now let's say we have, and I'm just going to use some generic numbers here. Sometimes when we don't have any matching numbers, it's easier to see where everything went. So now I've got the matrix with entries 1, 2, 3, 4, 5, 6, 7, 8, 9. That's my A matrix. And that's like the coefficient matrix that we've been working with in the last few sections. And then the X matrix, well, this A is a 3 by 3. It's got 3 columns, which means I have to multiply it by a vector in R3, which means our vector has to have 3 entries as well. So I'm going to have a vector that we're multiplying it by of -2, 4, -1. So this one's a different size, so we'll see how this one ends up a little different. Notice how in our first example our vector had 3 entries, but A was a different size. And that's okay, because the only part of A that matters is the number of columns. So the A in the first example had 3 columns, and the vector had 3 entries, and that's why it worked. Here in this next example, even though we now have 3 rows as opposed to 2, that's perfectly fine, as long as the number of columns in A matches the number of entries in your vector. This will work. So the way that we said this is going to play out is these values are weights for each of these columns. So we've got -2 times 1, 4, 7, and then 4 times 2, 5, 8, and then -1 times 3, 6, 9. And now we've just got scalar multiplication and addition in order to finish this out. So this turns into -2, -8, -14, plus 8, 20, and 32, plus, because I'm going to go ahead and distribute -1, -3, -6, -9. These will all be the same size, which means we can combine one step further and just either add or subtract corresponding entries. So I can add together the -2 and the 8 and the -3, and that's going to give me 3. And then 20, or -8, 20, and -6 is going to give me 6. And then -14, 32, and -9 is going to give me 9. I want to do one more quick example where we've got some variables. So this time, let's say we have the vector 5, 0, -1, 2, 3, 4. And we are going to multiply this by, now look at this matrix, it's a 3 by 2. It has 3 rows and 2 columns. So can you guess what size vector we're allowed to multiply it by? Well, remember in our definition, it was always each column that gets a weight from the vector. So if we have 2 columns in this matrix, that means our vector must have 2 entries. So this time I'm just going to use variables, v1 and v2 in my vector. And each column gets a weight from the vector. So v1, since it's the first entry in our vector, goes with the first column, 5, -1, 3. And then v2 goes with the second column, 0, 2, 4. And we can think of that as scalar multiplication. So 5v1, -v1, and 3v1. When I distribute my v2, I'm still going to get a 0 here, because v2 times 0 is 0. Then we have 2v2 and 4v2. And now I've got 2 matrices of the exact same size, and I can combine them. And I end up with 5v1 -v1 plus 2v2, and 3v1 plus 4v2. That's almost starting to look like a system of equations. So we're trying to figure out here how we can use these matrices and these vectors to help us represent systems of equations and use the coefficient matrix and the variable vector to write it a little bit differently and solve it a little bit differently. We're also going to try one of these backwards. We're going to try to write 9v1 minus 5v2 plus v3 as a matrix times a vector if v1, v2, and v3 are in Rm. Now remember what that means. That means that these guys are actually columns with m entries. We said this R notation, every time you saw a superscript on it, it just meant we're dealing with something that's a column vector that has that many entries in it. So v1, v2, v3, those are not just individual variables, those are columns with m entries. And the weights we have on these columns are 9, -5, and there's nothing there. So remember from algebra, we assume it's a 1. So we're going to separate this back out. We had said the weights come from our column vector that we have to write second. If we were to change the order of the a times the x, we would get a different answer. And then what we're multiplying those weights by, those individual columns, are v1, v2, v3. So your weights always go in a column vector and they always go second in the product. Now that we've done a few examples with the a times the x and how to multiply it and also how to pull them back apart, we've just got one more step to do what we said at the beginning of this section, which was figure out how to write ax equals b. So the only part we're missing is the equals b, and that's the part where the systems of linear equations come in. So for a system of linear equations, so the difference now is we're actually going to have these equal something. Up here they weren't equal to anything, I was just writing a product. So that's the a times x part. But for the system of linear equations, we can also throw in the equals b, where b is also going to be a vector. It's got a whole list of numbers arranged in a column. So consider the system of equations x1 minus, said 1, but I wrote 2, x1 minus 4x2 plus 2x3 equals 9, and then 2x1 plus x2 minus 5x3 equals 1. Now, those equations individually we could write as a times x. The new part is that we've got them equal to some value. So we were able, in the last section, when we were checking to see if a vector was a linear combination of a given set of vectors, we were able to start with just the vectors and then end up turning it into a system of equations. And we're pretty much going to just do that backwards here. So if you look at what we've got x1s lined up, we've got x2s lined up, we've got x3s lined up, and then we have solutions lined up. Each of these pieces is going to be separated out into their own little vector. So we're going to have x1 and 2x1. Those could go together. And then I've got negative 4x2 and x2. Those are the second entries. And then we've got 2x3 minus 5x3 equals 9, 1. Now each of these individual vectors on the left-hand side have something in common. In this first vector, both of the entries have an x1 in common. So I could factor it out, and that would leave me with 1, 2. In the second, they both have an x2. I can factor it out, and it leaves me with negative 4, 1, which are just the coefficients. And then that third matrix, or the third vector, they both have an x3 in common. And if I pull it out, I'm left with the coefficients of 2, negative 5. This is starting to look like one of the steps we talked about at the very beginning of the section when we were distributing weights to columns of a vector. So these here are serving as weights for those column vectors. And remember, the weights originally came from a vector in the second position of the product. So I can pull my weights back out as a vector, and I can squish my other vectors together into just one big matrix. And this is equal to 9, 1. So what we have here is A. That's a coefficient matrix. If you compare this with what we started with when it was just written as a system of algebraic equations, these are exactly the coefficients we had on x1, x2, x3. And then we've got our variable vector, and they got multiplied together, and that's equal to our constants, our solutions, which is our b vector. So every system of equations can be written as A times x equals b, where A is a coefficient matrix, we call x the variable vector. That's where all of our variables get stored, and it's a vector because it's just a column matrix. And then we have a solution vector. Let's look at another one of those real quick, and then we're going to do this one a lot quicker. Now that we have identified where all of those pieces come from, we should be able to do it faster. So what if we have 5x1 minus 3x2, 2x1 plus x2. Ooh. I'm using two different notations here. Right now I'm just writing out my system. x1 minus x2 equals 8. And then x1 plus 2x2s equals negative 2. we are going to write this in the form AX equals B. We're going to write it as the matrix equation AX equals B. The A is just the coefficient matrix. So if you look at the coefficients we have, and we keep them in the exact same order they're written because the system is already in standard form. We've already got all the x1s lined up, all the x2s lined up, all the variables are on the left, all the constants are on the right. So we've got 5, -3, 2, 1, 1, -1, 1, 2. Those are all of our coefficients for x1, x2. And then we've got a variable vector that distributes weights to these guys. And the first one goes in the first entry, and the second one goes in the second entry. And then we've got a solution vector, which is 12, 4, 8, -2. So we did this one a lot quicker than the last one, because on the last one we showed how it broke down into each individual step. But really you can look at a system and immediately jump to the AX equals B equation once you get comfortable with it. So this is our coefficient matrix A, this is our variable vector B, and this is our solution, our variable vector X and our solution vector B. So like I said earlier, what we're doing here is linked back to what we did in the last section, where we were trying to figure out if a given vector was a linear combination of another set of vectors. Another way of saying that is that a vector belongs to a span of vectors. And that was in section 1.3. We said if B is in the span of A1, A2, all the way out to AN, then we should be able to write that out as a matrix equation, a vector equation, and we could consolidate it down to this matrix equation, AX equals B. So with just the this kind of variable notation where we don't really know what these numbers are yet, we said that this would be true if AX equals B, which is another way we just learned how to write this, is a consistent system. And that means we are able to find a solution. So there's an interesting thing that comes about that if we just use a generic value for the B's, we can try to figure out if a particular system is consistent for all possible B values, where the B we're going to say is B1, B2, B3. So B is in R3. And this should say is here. If A is 215, -130, 9, negative 4, 1. If it's consistent for all possible B1, B2, B3, that means we have an infinite number of solutions. If there's not an infinite number of solutions, then we'll come up with an equation that that ties together our B1, B2, B3 that we have to make sure is always true. But the way that we can figure this out, this is technically just 2x1 plus x2 plus 5x3 equals B1, negative x1 plus 3x2 equals B2, 9x1 minus 4x2 plus x3 equals B3. All I've done is I've remembered that A is a coefficient matrix for the x's, and since I have 3 columns, there is going to be 3 variables, so I have an x1, x2, x3, and we're trying to figure out if this works for all b values or just a select number of b values. And we said if that's true, then it's going to be a consistent system. Well, let's go ahead and work out this augmented matrix and see what happens. The difference now is that we don't have actual b values. We're just working it out with those arbitrary b1, b2, b3 values. So this is 2, negative 1, 9, 1, 3, negative 4, 5, 0, 1. That's just our A value, our A matrix. And then if we were writing this system as an augmented matrix, we would just throw the B1, B2, B3 in the last column. And we want to work row echelon form on this matrix until we can kind of figure out what's happening with the B1, B2, B3. So the first thing I'm going to do is divide row 2 by 2. That's the same thing as row 1, a half row 1. And that will create my 1 here in row 1. So I've got 1, a half, 5 halves, and B1 over 2. At the same exact time, just to consolidate some space and some time, I now see that my row 2 and my row 1 have opposite coefficients. So if I now add them together, that will create a 0 under my first pivot position. So I want to add these new row 1 values with the row 2 values. So 1 and negative 1 is 0. A half and 3 is 7 halves. 5 halves and 0 is 5 halves. And then we've got B2 plus, and let me actually change the order so it is consistent with how we wrote it. This is going to be B1 over 2 plus B2. And now we also want a 0 in that last row under our first pivot position. So I'm going to do negative 9 row 1 plus row 3. Everything else is going to stay the same. So I get negative 9 plus 9 is 0. Negative 9 halves minus 4 is negative 17 halves. Negative 45 halves plus 1 is negative 43 halves. And then I've got negative 9b1 over 2 plus b3. Now we want to get a 1 in the first non-zero entry of the second row, and that's going to be our next pivot position. So to do that, I've just got to multiply by 2/7. And when I do it on the B entry here, in the last entry of that row, I'm going to go ahead and multiply the 2/7 to both pieces. And this ends up as B1 over 7 plus 2B2 over 7. That last column is going to start to get a little bit complicated, especially since we have fractions here. So just double check your work as you go if you're unsure. So now we've got our first pivot position and zeros underneath, so that one's done. I've created my second pivot position, so I'm going to get zeros underneath. So we're going to have to multiply row 2 by 17 halves. And add it to row 3 in order to make a 0 there in that third row. So 17 halves times 0 plus 0 is 0. 17 halves times 1 is 17 halves plus negative 17 halves is 0. 17 halves times 5/7, that's going to be 85 over 14. I need to add that to negative 43 halves. And at this point we definitely want to get our calculator out. And from my calculator I end up with negative 108 over 7. Now the B's is where it's going to get interesting. I've got to do 17 halves of this guy plus this guy. So because we've got variables, there's probably not going to be a whole lot of simplifying we could do. But if you need to write that out to the side, that might be helpful. I am going to go ahead and distribute because we're going to end up with some like terms that we can combine. So I have 17 halves times B1 over 7. That's going to be 17B1 over 14. And then 17 halves times 2B2 over 7. Those 2's are going to cancel. I'm going to have 17B2 over 7. And then I want to add to that what I already have in row 3, which is negative 9B1 over 2 plus B3. So there's two B1 terms there that we can put together. The 17B1 over 14 and the negative 9B1 over 2. So we'll get a common denominator of 14. And that's negative 63 plus 17. And after simplifying, I get negative 23/7 B1. And then the B2 and the B3, there's only one of each of those terms, so we don't combine it with anything. Well, this one's starting to get a little crazy, but that's okay, because when we look at applications in real life, they're never going to be simple, and they're never going to work out beautifully. So we now need a pivot position here in row 3. So we need to multiply row 3 by negative 7 over 108. Everything else is staying the same right now. I'm just manipulating row 3. So anything times 0 is going to leave those guys as 0. And we purposely did the reciprocal so that when we multiplied we'd get a 1. And then I've got to multiply this crazy expression back here by negative 7 over 108. Luckily it's not going to be too terrible, because the place where I have those two crazy fractions have denominators of 7, and I'm multiplying by something with a numerator of 7, so the 7's are just going to cancel out. So what I get is 23 over 108 B1 minus 17 over 108 B2 minus 7 over 108 B3. And we don't have to do reduced row echelon form. Row echelon form is fine. We can now see from this last row if we're going to have a solution or not. And we will, because we've got pivots in row 1, row 2, row 3, and we still have our solution column. So really at this point, 23 over 108, if you think about how this system ends up consistent, once you're in echelon form, you look at your last row, and what this says right now is that 0x1s, 0x2s, and 1x3 is equal to all this stuff. So really, this can be anything. Because we had a pivot position in row 3, that last B value that we ended up with could equal anything, and we would still get a solution. Now we're not going to continue on with this solution because it's so crazy. We've got such crazy numbers. But there's no restrictions on that last value if you have a pivot position there. It could equal 0, and that just means x3 equals 0. It could be anything else, and that just means x3 is equal to whatever that value is. So as this value here can be anything, and we would still get a solution. So what that means is, yes, this works for every value of B1, B2, B3. Because what we were asked at the beginning was, is AX equals B consistent for all possible B if A is 215, negative 130, 9, negative 41. And it will be, no matter what is in the B column. Our coefficient matrix gave us those ones on that diagonal, which is ideal. Ones on that diagonal right there means we'll always have a single solution. And this has an important result when we look at what's happening here geometrically. If we were to think of our A vector as being, breaking it out in columns, our A matrix broken out into columns will give us 3 individual vectors. And what we have proved is that those 3 vectors will always give you a solution, which means those 3 vectors span the entire 3-dimensional space. Those 3 vectors individually. And they were originally 2, negative 1, 9, 1, 3, negative 4, and 5, 0, 1. And I know I'm not going to remember these. 2, negative 1, 9, 1, 3, negative 4. And 5, 0, 1. We can make a combination of these 3 vectors equal any other 3-dimensional vector. That means they span the entire 3-dimensional space. Now, if we did not have that nice perfect diagonal there, the only reason we wouldn't is if this 3rd pivot position was a 0. And in order for this system to remain consistent, then this last entry in our B vector would also have to equal 0. And those would be the only combinations of B1, B2, B3 that would work, as if they satisfied that equation that we had. What that actually creates is a plane in three-dimensional space. So if our last row was 0, 0, 0 star, then the system would only be consistent if the star was equal to 0. This equation here creates a plane in three-dimensional space that all of our vectors span. So in this case, in our example, the B1, B2, B3 were not restricted at all. That means we span the entire three-dimensional space. If that last row was 0, 0, 0, then the only way it would be consistent is if the last value was also 0. Well, that last value, remember, was our really complicated B equation. So what we end up getting is an equation with three variables set equal to 0, and that's the equation of a plane in three-dimensional space. So our vectors that we started with would only span that particular plane in three-dimensional space. This concept is kind of confusing. I would like you to try this one on your own. So if A equals 5, 8, 7, 0, 1, negative 1, 1, 3, 0, is the matrix equation AX equals B consistent for all values of B? So either our answer is going to be yes. If for some reason we got no, if it's not, then what we do is we come up with an equation of a plane through the echelon process, row reduction, echelon form process, for the span of those columns of A. So I'm going to get you started with this, and then I want you to pause and try to finish the rest of it. So we've got our A. We can leave off the X. We're just going to write this as an augmented matrix. So we're going to have 5, 8, 7, and we don't know the B values. We're seeing if it works for all B values. 0, 1, negative 1, B2. And if it's easier for you, you can use ABC here in the last column, then you're not having to kind of wrestle with those subscripts. We want to get this matrix, so this is our A matrix augmented with B solution vector. We want to see if we end up with a pivot position along the diagonal. That is ideal. That means that those three column vectors are unique, and they will span all of R3, which means every single point in three-dimensional space can be made out of those vectors. If we don't have a pivot position in one of those spots, that means we're going to have to put some restrictions on the value in the last column in order for the system to be consistent. And that equation we get for the restrictions is the equation of the plane that our vectors span. So that would answer both of our questions here. Is it consistent for all values of B? If it is, we should get pivot positions on all of those, on that diagonal, those three that I circled blue. If we don't get pivot positions in those three spots, then the only way this is going to be consistent is on that last row when we have 0, 0, 0, if we make sure whatever ends up in the third position of that B column is equal to 0. And that's going to be a giant equation with B1s, B2s, B3s in it, and that is the equation of the plane that our column vectors do span. So that will answer the second question. So what I would like you to do is pause the video and get this matrix down to row echelon form. And once we have row echelon form, we can figure out, based on the entries in that last row, if it's going to be yes, it spans all of R3, and we can find any B solution vector we need to, or we're going to say no, it doesn't, and only this specific plane, and we'll write out the equation, is spanned by A, by the columns of A. So pause the video and see if you can get that down to row echelon form. And I say pause it because I am going to immediately jump to the row echelon form and show you what it is. And actually, since this is still pretty new to us, I think it would be beneficial for me to show you another one. So first thing I'm going to do is I'm going to swap row 1 and row 3. That's the easiest way to get a 1 in that first position. So 1, 3, 0, B3, 0, 1, negative 1, B2, 5, 8, 7, B1. So I've got my first pivot position, and I have already a 0 underneath it. I need a 0 in that third row. So I'm going to do negative 5, row 1 plus row 3. And if we do that, we'll get 0. Negative 15 plus 8 is negative 7. A 0 plus 7 is 7. And then negative 5 B3 plus B1. So we've got our first pivot, we've got our zeros underneath. Now we go on to our second column. And there's already a 1 in the spot that we want it. We just have to get a 0 underneath. So for my next step, I'm going to do 7 row 2 plus row 3. That'll get us a 0 underneath. So I'm going to end up with 7 times 0 plus 0. That's still 0. 7 plus negative 7 is 0. Negative 7 plus 7 is 0, and 7b2 plus all of that stuff. So that's 7b2 minus 5b3 plus b1. So this one was much easier, much quicker. And you look at your last row to see what's happening. We've got pivots exactly where we expect them in row 1 or row 2, but we don't have pivots along that nice diagonal, which is what we're looking for. So this system is only consistent if this value is 0. So we're going to say no, not every value of B will make the equation ax equals b consistent. Only when 7b2 minus 5b3 plus b1 equals 0. And that is the equation for a plane in three-dimensional space. And we can only create points on that plane using these column vectors in A.